Have you ever sat in an airplane, maybe, 35,000 feet up, sipping that slightly warm ginger ale,
Uh-huh.
and just thought, how on earth does this massive metal tube actually stay in the air, and what keeps it all, running so smoothly?
Yeah, it seems almost simple from the passenger seat, doesn't it?
Deceptively simple. But underneath, well, it's just an absolute marvel of engineering, a mind-boggling array of systems all working together.
Absolutely.
So today, that's what we're doing. We're taking a deep dive into our intricate world, the hidden complexities of turbine airplane aerodynamics, structures, and sternums.
Right.
Think of it like getting a shortcut, maybe a fast track, to understanding the core knowledge needed just to maintain these incredible machines.
And we're not just winging it, so to speak.
Oh, nice.
We're pulling our insights today straight from, well, the bedrock of aviation knowledge, EASA Module 11A.
Okay.
For anyone in the field, you'll know this is a really comprehensive technical guide. It's basically the foundation text for getting an aircraft maintenance license.
The real deal.
Exactly. It lays out all the essential knowledge, everything from, how a wing generates lift right through to the really sophisticated systems keeping us safe and comfortable up there.
Absolutely. So our mission today is pretty clear then. We're going to extract the most important nuggets of knowledge from this, well, frankly, incredibly dense material.
It is dense, yeah.
And translate that technical detail into something concise, but still thorough, an understanding of what really makes a modern airliner tick.
Giving you the core concepts.
Exactly. Consider this your express ticket to being genuinely well-informed about the machines connecting our world. Okay, let's unpack this.
The invisible forces and the unseen framework, aerodynamics, and structures.
All right, let's kick things off with what often feels like magic. How does a huge metal tube actually defy gravity and fly?
It really comes down to some, well, fundamental principles of aerodynamics, and crucially, a set of precisely controlled surfaces.
Surfaces, okay.
That's right. The directional control of a fixed-wing aircraft, banking, pitching up or down, moving left and right.
Yeah.
It all happens around its three primary axes.
The main ways it can move.
Exactly. And this control comes from various hinged or movable flight control surfaces. We usually split them into two main groups, primary and secondary.
Okay, and when we talk about those primary controls, we're talking about the real workhorses.
Yeah.
The surfaces that directly steer the plane.
Precisely. We mean the ailerons, the elevators, and the rudder. You can almost think of them as smaller wings themselves, smaller aerodynamic surfaces.
Right.
So ailerons, they're usually on the outer trailing edge of the wings. They control roll, that banking motion.
How did they do that?
They work differentially. So one goes down, the other goes up. This creates a difference in lift between the wings, and that makes the aircraft roll.
Clever.
Then you have elevators, typically on the horizontal part of the tail. They control pitch, moving the nose up or down.
Okay.
And the rudder on the vertical tail controls yaw. That's swinging the nose left or right.
Got it. And how are they built? Are they flimsy?
Oh, no, not at all. They need to be robust but also light, often built around a strong internal spar, kind of like a backbone, with ribs forming the shape and a lightweight skin, usually aluminum, attached. Similar construction to a small wing, really.
Okay, so those are the primaries, but you mentioned secondary or auxiliary surfaces too. What's their job? They're not just decorations, are they?
Definitely not. They're crucial. They augment the primary controls, especially in certain flight phases, like takeoff and landing.
Okay.
A big group here are the high-lift devices, things like flaps and slats.
Flaps, I see those extending when we land.
Exactly. Flaps are probably the most common. They extend from the trailing edge of the wing, the back edge.
And what do they actually do?
What they do is pretty brilliant, actually. They effectively increase the wing's curvature, its camber. This generates significantly more lift.
More lift. Okay.
Which means the aircraft can fly much slower, safely, during takeoff and landing. It drastically reduces the speed at which the wing would stall.
So the genius isn't just more lift, it's about fundamentally changing the wing's behavior, allowing this huge plane to sort of float at slower, safer speeds. That must have been a massive hurdle in early aviation.
It absolutely was. Managing those low-speed parts of flight safely and efficiently is key. And alongside flaps, you often find slats or slots on the leading edge, the front edge of the wing.
Slats and slots.
Yeah, these are incredibly clever, too. They open up a small gap. This lets high-speed airflow from underneath the wing flow over the top surface and mix with the slower air there.
What does that mixing do?
It energizes that slower boundary layer air. This helps keep the airflow attached to the wing surface for longer, delaying airflow separation.
Which delays the stall.
Exactly. It delays the stall. Fantastic for low-speed control. But there's always a trade-off.
Ah, there usually is.
Increased drag. That's the price you pay for that extra low-speed lift and control.
Makes sense.
And you'll often see wings designed so the root, the part closest to the fuselage, stalls before the wingtips.
Why?
It makes the stall much more manageable. The aircraft tends to pitch down gently, and crucially, you still have airflow over the ailerons out near the tips, so you retain roll control for recovery. Much safer.
Okay, so they help with lift at low speeds. What about slowing down once you're on the ground? Or even in the air?
Right. That's where drag-inducing devices come in. Things like speed brakes and lift dumpers.
Speed brakes, are those the panels that pop up on the wing?
Often, yes. Spoilers can act as speed brakes when deployed symmetrically on both wings. They create a lot of drag to slow the aircraft down, maybe for a steeper descent without gaining speed.
And lift dumpers. Sounds dramatic.
They are, in a way. They're similar surfaces, but they're designed to be deployed right after touchdown. They basically destroy the lift the wing is generating.
Why would you want to do that?
It puts more of the aircraft's weight firmly onto the wheels much faster. That gives you much better braking effectiveness right when you need it most.
Ah, smart. And what about the really fine adjustments? Keeping the plane flying straight and level without a pilot constantly wrestling with the controls. Trim controls.
Yes, trim control is absolutely essential for reducing pilot workload. Think of trim tabs. They're like tiny little flaps on the trailing edge of the main control surfaces, the elevator, rudder, ailerons.
Any flaps on the flaps?
Sort of. They create a small aerodynamic force that holds the main control surface in the position the pilot wants it. So if the pilot wants to climb gently, they adjust the elevator trim tab, and the tab holds the elevator slightly up.
So the pilot doesn't have to physically hold the pressure.
Exactly. It trims the aircraft for that flight condition. There are other clever types too, like balance tabs, which are linked mechanically to move in a way that helps the pilot move the main control surface, reducing the physical effort needed.
Makes it easier to fly.
And mass balance. That involves adding carefully placed weights inside the control surface itself, often in the leading edge. This prevents a dangerous aerodynamic flutter that can happen at high speeds. It's all about stability, control, and making the pilot's job easier.
Okay, now here's where I find it gets really fascinating. What happens when an aircraft gets close to the speed of sound? Not necessarily fighter jets, but even commercial airliners cruise pretty fast, right?
They certainly do.
I always hear terms like Mach crit, and it sounds like there's this, invisible wall they have to deal with. Can you break down what actually happens up there?
That's a great question. And yeah, it's a critical area in aerodynamics. Modern jets typically cruise somewhere between Mach 0.7 and Mach 0.9.
So 70 to 90% of the speed of sound.
Correct. But first, let's define some terms. The actual speed of sound isn't constant. It changes with altitude and temperature. Subsonic flight is simply flying slower than that local speed of sound. Supersonic is faster.
And transonic.
Transonic flight is that tricky region in between, where the airflow over some parts of the aircraft, maybe the top curve of the wing, reaches or exceeds Mach 1.0, even if the aircraft itself is still technically subsonic.
Ah, okay. And that leads to...
That leads us to the critical Mach number, or Mach crit. This is the precise flight speed where the airflow over any part of the aircraft first hits Mach 1.0. It's the boundary between subsonic and transonic flight for that specific aircraft design.
So once any part of the airflow hits Mach 1.0, even if the plane itself hasn't, what happens then? Does the plane just start shaking?
It can be much more serious than just shaking. When airflow accelerates locally to Mach 1.0 or beyond, it creates shock waves.
Like tiny sonic booms on the wing.
Exactly like that. These shock waves are abrupt changes in pressure and density. They can cause the airflow behind them to separate from the wing surface.
Airflow separation. Oh, that sounds bad.
It is. It leads to a loss of lift, a sudden increase in drag, and often compressibility buffet, which is a violent shaking of the aircraft. Control can become very difficult. It can feel like hitting an invisible wall.
Wow.
And in extreme cases, if the structure isn't designed for those loads, the forces could potentially cause structural failure. It's a serious phenomenon.
So how do engineers design commercial airliners to fly safely and efficiently right up near that Mach crit barrier?
One of the most ingenious and fundamental design solutions is wing sweep, or sweepback, sweeping the wings backwards.
Like you see on virtually all jetliners. Why does that help?
But sweeping the wings, you essentially trick the airflow. You make the wing believe it's flying slower than the aircraft actually is.
How does it do that?
It effectively reduces the speed of the airflow component that's flowing directly perpendicular to the wing's leading edge. It's this perpendicular flow that matters most for compressibility effects.
Oh.
So, wing sweep delays the formation of those problematic shock waves and pushes the onset of compressibility effects of the buffet, the drag rise to a higher aircraft Mach number.
Allowing them to fly faster.
Faster and more efficiently, without encountering those severe control issues. It really softens those aerodynamic changes, making high subsonic flight smooth and safe.
Okay, that makes sense. Moving from how it flies through the air to, well, what it's actually made of. Once you've designed a wing shape for high speed, what are the core philosophies behind designing the aircraft's body, its airframe?
Right, the structure itself. Modern aircraft design philosophy heavily emphasizes damage tolerance.
Damage tolerance, as opposed to what?
As opposed to the older concept of fail-safe. Fail-safe meant that if one component failed, another would take the load. Damage tolerance takes it further. It assumes that small flaws or damage, like fatigue cracks, might exist in the structure, perhaps undetected between inspection. So the structure is designed such that even with that assumed damage, it can still safely carry the expected flight loads until the damage is detected during routine maintenance and repaired. It's about ensuring integrity even with potential hidden flaws.
That sounds much more robust. So for maintenance, how do technicians pinpoint exactly where a specific part or potential problem area is on such a huge, complex structure? It sounds difficult.
It would be, but manufacturers use very precise zonal and station identification systems. Think of it like a grid reference system for the entire aircraft. They use numbering systems, often starting with a 0 station, maybe at the nose, and then measuring distances in inches or millimeters back from there. There are specific station identifiers for wings, stabilizers, engine nacelles, everything.
So everyone knows exactly what fuselage station 450 means.
Exactly. It allows for absolute precision in maintenance instructions, locating components, tracking repairs. It's fundamental.
We often hear about stress and strain acting on aircraft structures. Are they the same thing?
They're closely related but distinct. Think of it this way. Stress is the internal force within the material that resists being deformed by an external load. It's the material fighting back, measured in force per unit area, like SI.
Okay. The internal resistance?
Right. Strain, on the other hand, is the actual deformation or change in shape that occurs because of that stress. It's usually measured as a ratio, like the change in length divided by the original length.
Yeah.
So the external load causes internal stress, and that stress causes the material to strain or deform.
Got it. And what kinds of stresses are we talking about on an airplane?
Aircraft structures experience 5 main types. There's tension, which is a pulling force trying to stretch the material. Compression, a pushing or squeezing force. Shear, which is like a cutting force trying to slide layers past each other. Torsion, which is a twisting force.
Like wringing out a towel.
Exactly.
Yeah.
And very commonly, bending. Bending is actually a combination stress. When a wing bends upwards in flight, the top surface is in compression and the bottom surface is in tension.
Wow, okay. So how do manufacturers prove that these structures can handle all those stresses, cycle after cycle, for decades, without failing from fatigue?
Through incredibly rigorous fatigue testing. This isn't just calculations. They build full-scale test structures, sometimes entire airframes.
The whole plane.
Sometimes, yes, or major sections like the wing and fuselage assembly. They put these structures onto massive hydraulic rigs.
And then they just shake them.
They apply cycles of loads, pushing, pulling, twisting, simulating maybe 2 or 3 times the expected service life of the aircraft. They deliberately introduce artificial flaws sometimes to test the damage tolerance principles. They monitor crack growth. It's all about proving physically that the structure meets and exceeds its design life requirements.
That's reassuring. Now, beyond just holding together, what about electrical continuity? And battling corrosion, which must be a constant fight.
2 huge areas.
Yeah.
Bonding is absolutely critical. This means electrically connecting all the metallic parts of the aircraft together,
Why is that so important?
primarily for lightning protection. If lightning strikes, you want that massive electrical energy to flow smoothly over the entire surface of the aircraft without creating sparks or high voltages between different parts. Good bonding ensures this.
Where does the lightning go then?
It dissipates back into the atmosphere, usually through static dischargers or static wicks. These are those little pointed rods you see on the trailing edges of wings and tail surfaces. They help bleed off static charge buildup too, which prevents interference with radios and navigation systems.
And technicians check this bonding.
Regularly. They use special meters to measure the electrical resistance between components, ensuring it's extremely low, typically less than 0.1 ohm for bonding jumpers, for example.
Okay. And corrosion prevention. Given that planes fly through rain, clouds, salt air near coasts, it seems like a recipe for rust.
It is a constant battle. Good design helps a lot about olds. Things like making sure there are adequate drain paths for water to escape, avoiding places where moisture can get trapped, using sealants during assembly.
But the metal itself needs protection.
Absolutely. One common technique is cladding, especially with aluminum alloys. They roll a very thin layer of pure aluminum onto the surface of the stronger alloy sheet. This pure aluminum naturally forms a tough, protective aluminum oxide layer. That's what alclad is.
Ah.
Proper surface cleaning and treatments are also vital. Using only manufacturer-approved chemicals is critical because the wrong stripper or cleaner could actually damage the metal or cause hydrogen embrittlement, making it brittle. It's a meticulous process involving stripping old paint, sometimes applying chemical conversion coatings like allodyne, and then repainting.
How do they ensure an aircraft is perfectly straight and aligned, structurally speaking, especially after maybe a major repair?
Through airframe symmetry checks. It's about ensuring everything is positioned correctly relative to the aircraft's main reference lines, the longitudinal center line, and lateral datum lines.
How do they check that?
It depends on the aircraft size. For smaller planes, it might involve using plumb bobs, spirit levels, and precise measurements from reference points. For large transport aircraft, it's often more complex, using optical alignment tools or even laser trackers, sometimes referred to as a grid method, to check the position of key points with extreme accuracy. The aircraft has to be properly jacked and leveled first, of course.
Let's zoom in on the main body, the fuselage. What's the dominant construction method for a modern airliner?
Overwhelmingly, it's semi-monocoque construction.
Semi-monocoque. Break that down.
Okay, monocoque would mean the skin alone carries all the loads, like an eggshell. That's not practical for large aircraft. Semi-monocoque means the skin does carry a significant portion of the load. It's stressed, but is reinforced internally by a strong framework.
What kind of framework?
It consists of bulkheads and frames, which run around the circumference, giving the fuselage its shape, and longerons and stringers, which run lengthwise, stiffening the skin against buckling. This combination creates a very strong, yet relatively lightweight and damage-tolerant structure. Loads are distributed through multiple paths.
So if one part fails, the load finds another way.
Exactly. It's inherently fail-safe. Most airliners have this tubular fuselage, often with an oval or circular cross-section, which is ideal for handling pressurization loads. Any major cutouts for the wings, landing gear, doors, windows have significant extra reinforcement around them to maintain structural integrity.
And how do the wings, carrying all that lift, actually attach to this fuselage structure?
They attach to heavily reinforced fuselage frames or bulkheads. The wing's main structural members, the spars, typically extend into the fuselage structure or attach via very strong fittings and bolts. It's a critical load path. The horizontal and vertical stabilizers attach in a similar robust manner, often bolted directly to reinforced frames in the rear fuselage.
What about the engines? They're hanging off structures called pylons, right?
Yes, pylons are the structures that attach the engines, usually under the wing or sometimes on the rear fuselage. These aren't simple brackets. They are complex, highly stressed structures themselves, often connecting to the wing's main spar and other strong points. They also house various systems, lines, fuel, hydraulics, electrics running to the engine, and incorporate firewalls for safety.
Inside the cabin, things like seats, galleys, they seem straightforward, but I guess they have structural considerations too.
They absolutely do. Passenger seats lock into seat frame tracks running along the cabin floor. These tracks and the seat attachments are designed to withstand very high G-forces during turbulence or emergency landings. Galleys, lavatories, even cabin dividers are all securely attached to the aircraft structure.
And cabin doors, they seem complex, especially with the emergency slides.
Very complex. Cabin entry doors have to seal perfectly for pressurization, open easily, but also incorporate the emergency escape slide system. There's a critical mechanism called the girt bar. When the door is armed for departure, this bar is attached to the fuselage floor brackets. If the door is then opened in an emergency, the girt bar pulls the slide out of its pack and initiates inflation. Ensuring that bar is correctly stowed when not armed and correctly attached when armed is a vital safety check.
And lastly, those windows and the big windscreen up front, are they just thick plastic?
Not quite, especially on pressurized aircraft. On small, unpressurized planes, windows might be single-pane acrylic. But on airliners, passenger windows are typically multi-layered for fail-safe redundancy. There are usually two structural panes, each capable of holding the pressure difference, plus an inner non-structural scratch pane for protection and noise reduction.
And the windscreen.
The flight deck windscreen panels are even more robust. They're multi-layered assemblies, often combining glass and plastic layers, designed to withstand bird strikes at high speed. And crucially, they contain embedded heating elements to prevent ice and fog formation, ensuring clear visibility for the pilots at all times.
Comfort, safety, and survival environmental and fire systems.
Okay, let's talk about comfort. It's easy to take for granted, isn't it? That environment inside the cabin, fresh air, the right temperature, being able to breathe normally at 75,000 feet. But making that happen is incredibly complex.
It really is a sophisticated operation. The air for both cabin pressurization and air conditioning primarily comes from the engines. It's called engine bleed air.
Bleed air. Where does it come from?
It's tapped off or bled from the compressor sections of the main turbine engines. This air is already highly compressed, which is useful, but it's also extremely hot because of that compression.
So you can't just pump it straight into the cabin.
Absolutely not. It would cook everyone. So before it gets anywhere near the passengers, it has to be processed and cooled significantly. When the main engines aren't running, like on the ground, the auxiliary power unit, APU, that small jet engine, usually in the tail, can provide this bleed air, or sometimes a ground air cart is connected.
Okay, so how do they cool down that super hot bleed air to make it comfortable?
On most commercial transport aircraft, this is done by the air conditioning systems, often referred to as packs. Typically, there are 2 or more packs for redundancy.
Yeah, how does a pack work?
They are usually air cycle systems. The hot bleed air first passes through heat exchangers, which work like radiators, using cold outside air, ram air, to cool the bleed air down somewhat. Then the core of the system is often an air cycle machine, ACM.
Okay.
Inside the ACM, the air might be compressed again slightly, which heats it up more, but then it passes through another heat exchanger, and finally it's expanded rapidly through a turbine.
Like a small jet engine running in reverse?
In principle, yes. As the air expands through the turbine, its pressure and temperature drop dramatically. This expansion is what provides the primary cooling effect. The energy extracted by the turbine often helps drive the compressor within the same ACM unit.
Efficient. What about humidity? Airplane air often feels dry.
It can, yes. As the air cools down significantly in the pack, its ability to hold moisture decreases. Much of the water vapor condenses out. The packs include a water separator specifically to remove this condensed water before the air is sent to the cabin. This prevents fogging or dripping in the cabin, but it does contribute to that low humidity feel.
Okay, so that's the air conditioning. What about cabin pressurization itself? Keeping the pressure inside comfortable while it's near vacuum outside.
Right. The aircraft fuselage, or at least the cabin and flight deck sections, is designed as a sealed pressure vessel. All the doors, windows, hatches, and even small openings for wiring or ducts have seals, compressible seals, grommets, sealants to make it as airtight as possible.
But it can't be perfectly sealed, can it?
No, there's always some leakage. But the key is that conditioned air is constantly pumped into this sealed area from the AC packs at a controlled rate.
And the pressure is controlled how? By pumping more air in.
Actually, no. The inflow from the packs is usually relatively constant. Pressure control is achieved by regulating how much air is allowed to leave the cabin.
Controlling the outflow.
Exactly. There are 1 or more outflow valves, typically large valves located towards the rear of the pressure vessel. These valves are automatically modulated, opened, or closed slightly to maintain the desired cabin pressure, or more accurately, the desired pressure differential between the inside and outside.
I know pressure drops fast as you go higher. How does that affect things? And were there challenges with this early on?
Oh, absolutely. Atmospheric pressure drops dramatically. At sea level, it's around 14.7 psi. At a typical cruise altitude of, say, 35,000 to 40,000 feet, the outside pressure is only about 3 to 4 psi. Without pressurization, humans simply couldn't survive up there for more than a few moments.
So the cabin isn't kept at sea level pressure?
No, maintaining sea level pressure would put enormous stress on the fuselage structure. Instead, the cabin is typically pressurized to an equivalent altitude of maybe 6,000 to 8,000 feet. It's a compromise between passenger comfort and structural limits.
And the historical challenge.
Metal fatigue. In the early days of jet travel, like with the de Havilland Comet, The repeated stress cycles of pressurizing the fuselage on every flight, then depressurizing, caused fatigue cracks to grow much faster than anticipated, leading to catastrophic structural failures.
Wow.
It was a harsh lesson that led directly to much more rigorous fatigue testing and the development of damage tolerance design principles we talked about earlier. Modern airframes are built to withstand hundreds of thousands of these pressure cycles.
So how do the pilots or the automated systems actually manage this pressure? Is it automatic?
It's highly automated now. The cabin pressure controller is the brain of the system. Modern controllers are typically electronic, though they often have pneumatic backups.
What do the pilots set?
They usually set the planned cruise altitude and the destination airport elevation before the flight. The controller then automatically manages the cabin pressure schedule, pressurizing gradually during climb, maintaining the target cabin altitude during cruise, usually aiming for a comfortable differential pressure, and then depressurizing gradually during descent, so the cabin pressure matches the outside pressure upon landing.
Smooths it out for our ears.
Exactly. It also controls the rate of pressure change to keep it comfortable. Pilots can monitor it all, usually on the ICAS or ECAM displays, and there are manual override capabilities if needed.
Okay, shifting gears now to an even more critical safety system. Fire protection. What's involved in detecting and putting out fires on board?
Fire protection is obviously paramount. It's evolved hugely from the days when crews just had to rely on seeing smoke or flames. Today's systems use sophisticated, reliable detection systems.
What kinds of detectors are used, and how do they avoid false alarms, which could be really disruptive?
That's the key challenge. High reliability and no false warnings under any normal or abnormal operating condition. That's the design goal. Several types of detectors are used depending on the location.
Like where?
In areas like engine nacelles or APU compartments, you might find thermal switches that close a circuit at a preset temperature, or thermocouples, which are very good at detecting a rapid rate of temperature rise, indicating a fire starting, rather than just a slow overheat.
How do thermocouples do that?
They typically compare the temperature of a hot junction exposed to the potential fire zone with a shielded reference junction. If the hot junction heats up much faster, it generates a small electrical current that triggers the alarm.
Clever. What about in cargo holds?
For cargo compartments and also lavatories, smoke detectors are essential. These usually work by drawing air samples through small tubes from various points in the compartment into a central detector unit. Optical or ionization sensors then check for smoke particles.
And if a fire is detected, say, in an engine, what happens next?
Then the fire extinguishing systems swing into action. While cabins have standard water or halon hand extinguishers for passenger use fires, the critical areas like engines, APUs, cargo bays, and even lavatory waste bins have fixed extinguishing systems.
What agent do they use? Is it like a sprinkler system?
Not usually water in those areas. The most common agent in modern fixed systems is halon, specifically halon 1301 or 1211. It's a very effective, clean agent that suppresses fire by interrupting the chemical chain reaction, and it doesn't leave residue or damage equipment significantly.
Okay. And how's it deployed?
In engine and APU compartments, they typically use high rate of discharge HRD systems. These involve pressurized bottles containing the halon. When activated, an explosive squib fires, rupturing a seal, and the agent floods the compartment extremely quickly, often within 1 to 2 seconds, to knock down the fire immediately.
And what happens when a pilot pulls that big red engine fire switch or handle in the cockpit? It looks like more than just triggering the extinguisher.
It absolutely is. Pulling that fire switch or handle initiates a critical sequence of actions designed to isolate the fire and starve it of fuel and air.
Like what?
Typically, it will shut off the fuel supply to that engine, close the bleed air valve from that engine, shut off hydraulic fluid supply, de-energize the engine's electrical generator, basically isolating it completely from the rest of the aircraft systems.
Cuts off everything that could feed the fire.
Precisely. And then, usually by rotating the handle or pushing a separate button, it discharges the fire extinguisher agent into that engine nacelle. Many systems have 2 shots of agent for redundancy.
What about cargo fires? Is it the same quick dump?
Sometimes it's a quick dump, especially for smaller compartments. But for larger cargo holds, you often see metered systems. These release an initial high concentration of agent to knock down the fire, and then continue to release the agent at a slower rate over a longer period, maybe up to an hour or more.
Why the slow release?
Because cargo compartments are large and often sealed. The idea is to maintain a fire-suppressing concentration of the agent for long enough to allow the aircraft to land safely, even if the fire isn't completely extinguished initially. It's about containment and buying time.
the intelligence and power grid avionics and electrical systems.
All right, let's look at it from the pilot seat now. That instrument panel, the flight deck, it's their window into everything the aircraft is doing. How is all that critical information generated and displayed?
You're right, it's the central hub. And fundamentally, even in the most modern glass cockpit with all the screens, any instrument system boils down to two main parts. A mechanism that senses something: pressure, temperature, attitude, and a mechanism that displays that information to the crew.
And they still use that T layout, don't they?
Yes, the basic T arrangement for the primary flight instruments is still standard. Your attitude indicator, artificial horizon, is central, airspeed to the left, altimeter to the right, and heading indicator below. It's designed for quick, intuitive scanning.
What are the main categories of instruments, and why is backup so important?
Broadly, you have flight instruments, the ones for controlling the aircraft's path, like the altimeter, airspeed indicator, attitude indicator, heading indicator, vertical speed indicator. Then you have engine instruments monitoring the power plants, things like RPM, temperature, pressure, fuel flow.
And systems instruments too, presumably.
Exactly, monitoring hydraulics, electrics, fuel quantity, cabin pressure, and so on.
Huh.
Redundancy is absolutely critical. With so many systems relying on electrical power and digital data buses now,
What happens if the power goes out?
well, that's why most aircraft, even highly modern ones, retain some key independent non-electric backup instruments. Typically a pneumatic altimeter, a pneumatic airspeed indicator, and a gyroscopic attitude indicator, plus a traditional magnetic compass. These ensure the pilots have basic attitude, altitude, speed, and direction information, even in a major electrical failure.
Okay, so how do these instruments actually sense things like pressure or temperature? How does an altimeter know the altitude?
Many traditional pressure instruments, like altimeters and airspeed indicators, rely on aneroid capsules, or bellows. Think of a small, sealed metal can that's very sensitive to changes in air pressure.
Like a tiny accordion.
Exactly. For an altimeter, this capsule is connected to the static pressure port, which senses the ambient air pressure outside the aircraft. As the aircraft climbs and pressure decreases, the capsule expands. This mechanical movement is then amplified through gears and linkages to turn the pointer on the instrument face.
Simple but effective.
It is. For airspeed, the indicator compares the static pressure with the ram air pressure coming from the pitot tube, that forward-facing probe. The difference between these two pressures, dynamic pressure, is directly related to airspeed.
What about modern systems? Is it still all mechanical bellows?
Increasingly, no. Modern aircraft use air data computers, ADCs, or digital air data computers, the ADCs. These receive pressure inputs from pitot tubes and static ports, but also temperature inputs from outside air temperature sensors.
Why temperature?
Because air density changes with temperature, and that affects the relationship between pressure and true airspeed or altitude. The ADC performs complex calculations, correcting for these factors, and then sends precise digital data, altitude, airspeed, vertical speed, temperature to the cockpit displays and other systems like the autopilot and flight management computer.
Much more accurate, I imagine.
Significantly more accurate, especially across a wide range of speeds and altitudes.
What about sensing the aircraft's attitude? Is it leaning left or right, nose up or down, and direction?
Attitude and direction rely heavily on gyroscopic instruments, or their modern solid-state equivalents.
Gyros, what's special about them?
Gyroscopes rely on two key principles. First, rigidity in space. A rapidly spinning rotor tries to maintain its orientation in space, regardless of how it's mounting the aircraft, moves around it. Second, precession. If you try to tilt a spinning gyro, it reacts with a force 90 degrees to the direction of the applied force.
How does that help?
For an attitude indicator, or artificial horizon, a gyro is set up with its spin axis vertical. As the aircraft pitches or rolls around it, the gyro stays stable, and linkages move a symbolic horizon bar relative to a fixed aircraft symbol, showing the pilot their attitude. For a directional gyro, DG, or heading indicator, the gyro spin axis is horizontal, providing a stable directional reference, much more stable than a magnetic compass, which is prone to swinging and errors during turns.
Are they still using actual spinning mechanical gyros?
Many aircraft still do, often powered by vacuum or electricity. But increasingly, modern systems use ring laser gyros, RLGs, or micro-electromechanical systems, MEMS gyros. These have no moving parts, relying on laser beams or tiny vibrating structures to sense rotation. They are much more reliable, lighter, and require less maintenance. Often, these sensors are part of an inertial reference system, IRS, or attitude heading reference system, HRS, which provides a complete package of attitude, heading, and acceleration data.
Okay, and what about angle of attack, AOA? You mentioned it earlier for stall warning. How is that sensed?
AOA is crucial. It's the angle between the wing chord line and the oncoming airflow. It's the primary indicator of how close the wing is to stalling. It's not the same as pitch attitude.
Right.
AOA sensors are typically small vanes or probes mounted on the side of the fuselage that align themselves with the local airflow. The angle of this vane is measured electrically and sent to the cockpit displays or stall warning system.
And that triggers the warnings.
Exactly. At specific, predetermined AOA values, the system activates the stick shaker of physical vibration of the control column as an urgent warning. Some aircraft also have a stick pusher, which automatically applies forward control pressure to lower the nose and reduce the AOA if the pilot doesn't react to the shaker, preventing a stall.
That brings us back to automation. How much of the flying, especially on a long-haul flight, is actually done by the aircraft itself these days?
A significant amount, thanks to sophisticated automated flight control systems, AFCS, or autopilots.
What can they actually do? Just hold a heading and altitude?
Oh, much more than that now. Basic autopilots can certainly do that. They use inputs from gyros or inertial systems to detect deviations from the selected heading or altitude and command the servos to move the control surfaces, ailerons, elevators, rudder, to correct the deviation.
But modern ones go further.
Absolutely. Advanced AFCS are integrated with the Flight Management System, FMS. They can automatically fly complex programmed routes, including climbs, descents, holding patterns, and approaches. They can manage airspeed using auto-throttle systems. Some can perform fully automatic landings, auto-land, in very low visibility conditions.
Wow. So the pilot is more of a systems manager.
In many phases of flight, yes. They program the system, monitor its performance, and are always ready to take over instantly if needed. But the autopilot handles the precise, continuous adjustments required to fly the aircraft smoothly and efficiently along the desired path. Many systems also include a flight director.
What does that do?
The flight director doesn't fly the plane itself, but it calculates the necessary pitch and roll commands to follow a selected mode, like intercepting a navigation course or following an ILS approach path. It displays these commands visually, usually as command bars on the attitude indicator. The pilot, or the autopilot if engaged, then flaws the aircraft symbol to match the command bars. It's a powerful guidance tool.
Okay, communication and navigation. How do planes talk to each other and the ground and find their way?
For voice communication, the workhorse is VHF radio for line-of-sight communication with air traffic control and other aircraft. For long distances, especially over oceans, HF radio is used, which can bounce signals off the ionosphere. There are also interphone systems for communication within the aircraft.
And navigation. Beyond just the compass and gyros?
Navigation relies on a suite of radio navigation aids and satellite systems. VOR, VHF omnidirectional range. Stations on the ground transmit signals that allow the aircraft to determine its bearing from or to the station. The ILS, Instrument Landing System, provides precise guidance for landing. The localizer beam gives left-right guidance along the runway center line, and the glide slope beam provides vertical guidance for the correct descent path.
I've heard of DME too.
Yes, DME, distance measuring equipment, is often co-located with VOR or ILS. The aircraft sends a signal to the ground station, which replies, and by measuring the time delay, the aircraft calculates its land range distance to the station.
What about avoiding other traffic?
That's where the transponder and TCAS, traffic collision avoidance system, come in. The transponder is a radio receiver transmitter that replies to interrogations from ground-based secondary surveillance radar, SSR, providing the aircraft's identity and altitude.
NECTA.
TCAS takes it a step further. TCAS-equipped aircraft actively interrogate the transponders of nearby aircraft. It analyzes the replies to determine their range, bearing, and relative altitude.
And warns the pilot.
Yes. If a potential conflict is detected, it issues a traffic advisory, TA, an audible alert and visual indication of the nearby traffic. If the risk becomes critical, more advanced TCAS-2 systems issue a resolution advisory, RA, a specific command like climb, climb, or descend, descend, telling the pilot exactly what vertical maneuver to perform to avoid collision.
And pilots have to follow that RA.
Yes. A TCAS RA takes precedence over any ATC instruction. It's a last line of defense against mid-air collision.
What's the next generation of traffic awareness?
That's ADSB, Automatic Dependent Surveillance Broadcast. Instead of relying on interrogation, ADSB-equipped aircraft automatically broadcast their precise GPS-derived position, altitude, velocity, and identity multiple times per second.
So everyone knows where everyone else is?
Yeah, essentially, yes. Other aircraft equipped with ADSB and receivers can display this traffic directly on their navigation displays, providing much better situational awareness than TCS alone. Air traffic control also uses ADS-B for surveillance, allowing for more efficient routing and closer spacing in non-radar airspace.
And for navigation itself, GPS is king now.
GPS, Global Positioning System, augmented by systems like WAAS, Wide Area Augmentation System in North America, or EASA in Europe, provides incredibly accurate position information worldwide. This enables RNAV, area navigation, approaches to runways without traditional ground-based aids like ILS, and allows for more direct and efficient routing. For very long-range flights, especially over oceans, large aircraft still rely on highly accurate inertial navigation systems, INS, or inertial reference systems, IRS, which use gyros and accelerometers to calculate position continuously without external references, though they are usually updated periodically by GPS.
Okay, powering all of this, the avionics, the flight controls, the cabin lights, everything requires a massive electrical system. What's the difference between, say, a small Cessna and a Boeing 787 in terms of power?
The difference is immense. A small Cessna might have a relatively simple 14-volt or 28-volt DC system powered by an engine-driven alternator and a battery. A large airliner like a 787 has a highly complex system generating both AC and DC power, often at multiple voltage levels, with extensive redundancy and sophisticated control and distribution networks.
Let's start with batteries. What types are used?
Traditionally, lead-acid batteries were common, similar to car batteries but aircraft grade. Then nickel-cadmium state batteries became widespread, offering better power density but requiring careful charging and monitoring to prevent thermal runaway.
And the newest?
Lithium-ion batteries are the latest certified technology used on aircraft like the 787. They offer significant advantages in terms of energy density, more power for less weight, longer life, and slower self-discharge. However, they also require very sophisticated battery management systems to ensure safety due to their high energy content.
Are batteries the main power source in flight?
No. Batteries are primarily for starting the engines, or APU, and for providing emergency power if the main generators fail. The main power generation in flight comes from engine-driven generators.
Generators or alternators?
On modern airliners, they are typically AC generators, often called alternators. A key component associated with them is the constant speed drive, CSD, or an integrated drive generator, IDG, which combines the drive and generator in one unit.
Why constant speed?
Because AC power frequency is directly related to the generator's rotation speed. Aircraft electrical systems require a very stable frequency, typically 400 Hz cycles per second, which is much higher than the 50 or 60 Hz used in homes. The CSD is essentially a hydraulic transmission that takes the varying speed from the engine gearbox and outputs a constant speed to drive the generator, ensuring that stable 400 Hz frequency regardless of engine thrust setting.
What if all engines fail? Is there backup power?
Yes. Besides the batteries, most airliners have a ram air turbine, RAT. This is a small turbine with a propeller that can be deployed into the airstream in an emergency. The airflow spins the turbine, which drives a hydraulic pump or an electrical generator to provide essential power for flight controls and critical instruments if all other power sources are lost.
How is all this power managed and protected?
Through complex control units. The Generator Control Unit, GCU, regulates the output voltage and frequency of its associated generator, protects it from faults like overloads or short circuits, and controls its connection to the electrical buses. The Bus Power Control Unit, BPCU, manages the distribution of power from the generators and other sources to the various electrical buses, main buses, essential buses, emergency buses, and controls the switching logic for redundancy.
So multiple generators work together?
Often, yes. Generators are frequently operated in parallel, sharing the load. The control systems ensure they synchronize correctly and share the load evenly. If one generator fails, the system automatically isolates it and redistributes the load among the remaining generators or sheds non-essential loads if necessary, ensuring critical systems remain powered. Redundancy is designed at every level.
The essentials of movement and protection, landing gear, fuel, and other systems.
Okay. We spend most of the time flying high, but eventually we have to come back to Earth. The landing gear, that's what connects us to the ground. It looks simple, just wheels on sticks, but it's obviously much more than that.
Oh, far more. The landing gear system is a critical piece of engineering, handling enormous static and dynamic loads. The main components are the gear structure itself, the retraction extension mechanism, the wheels and tires, the brakes, and crucially, the shock struts.
Shock struts? Are they like shock absorbers on a car?
Similar principle, but much more heavy-duty. They're typically oleo-pneumatic struts, meaning they use a combination of hydraulic fluid, oil, and compressed gas, usually nitrogen.
How does that combination work?
When the aircraft lands, the strut compresses. This forces the hydraulic fluid through a small, precisely shaped opening called an orifice. Often there's a metering pin that changes the size of this orifice as the strut compresses. This restriction controls the rate of fluid flow, smoothly dissipating the landing energy as heat in the fluid. The compressed nitrogen acts like a spring, supporting the aircraft's static weight and re-extending the strut after the initial impact.
What about steering and preventing wobble on the ground?
The nose gear typically incorporates a steering mechanism, often hydraulically powered. To prevent uncontrolled side-to-side oscillations, or shimmies, especially during takeoff and landing rolls, nose gear struts usually have shimmy dampers, either internal or external hydraulic dampers. They also have centering cams or internal mechanisms that automatically align the nose wheels straight ahead just before they retract into the wheel well.
What powers the gear retraction and extension? Seems like it would take a lot of force.
It does. It's almost always hydraulic power on transport category aircraft. A complex sequence of hydraulic valves directs fluid to actuators that unlock, move, and lock the gear.
And the doors covering the gear wells.
They're part of the sequence too. The gear doors have to open before the gear starts extending and usually close after the gear is fully retracted to maintain aerodynamics. This intricate timing is controlled by sequence valves within the hydraulic system, ensuring nothing collides. There are also uplocks and downlocks to hold the gear securely in the retracted or extended position, along with sensors and cockpit indications to confirm the gear status.
What kind of indications?
Typically, you have the classic landing gear lights. Green usually means down and locked, red means unsafe or in transit, and no light often means up and locked. Modern displays provide more detailed schematic views showing the position of each gear leg and the doors.
Okay, moving down to the wheels and brakes. Bringing tons of metal hurtling down a runway to a safe stop. How do the brakes handle that energy?
Aircraft brakes are incredibly powerful heat-dissipating devices. While smaller aircraft might use single or dual-disc brakes similar to cars, large aircraft almost exclusively use multiple-disc brakes.
How are they different?
They consist of a stack of alternating discs. Rotors are keyed to the rotating wheel hub, and stators are keyed to the stationary axle or torque tube. When brake pressure is applied, hydraulic pistons squeeze this entire stack together,
Creating friction between all those discs.
Exactly. Massive amounts of friction, converting the aircraft's kinetic energy into heat within the brake discs. Traditionally, these discs were made of steel, but most modern airliners now use carbon composite brakes.
Why carbon?
Carbon brakes are significantly lighter than steel brakes for the same stopping power, and they can absorb much more heat without fading or warping. They last longer too, although they are more expensive initially.
What prevents the wheels locking up during hard braking? Like
Like-
ABS in a car.
Precisely. It's the anti-skid system. Each main wheel has a wheel speed sensor, usually an electrical generator or sensor that produces a signal proportional to how fast the wheel is rotating.
Okay.
This signal goes to an anti-skid control unit. The unit compares the speed of each wheel to a reference speed, often derived from the other wheels or the aircraft's inertial data. If it detects that a wheel is decelerating too rapidly, indicating an impending skid or lockup, it instantly commands a control valve to reduce brake pressure to that specific wheel only.
Just for a moment.
Just for a fraction of a second, allowing the wheel to spin up again. Then it reapplies the pressure. This rapid modulation happens many times per second, keeping each wheel braking right at the point of maximum effectiveness, just below skidding. It maximizes stopping power and maintains directional control, especially on contaminated runways.
Essential tech. And finally, the tires. They take a beating, don't they?
They really do. They're the only contact point with the ground, handling huge loads, high speeds, extreme temperatures, and abrasion. Aircraft tire construction is highly specialized, with multiple layers of rubber compounds, reinforcing fabric plies, and strong steel wire beads to hold the tire onto the wheel rim.
How critical is inflation pressure?
Absolutely critical. Tires must be inflated to the correct pressure, usually checked daily or before the first flight, using dry nitrogen to minimize moisture contamination. Underinflation is particularly dangerous. It causes excessive flexing of the sidewalls, leading to rapid heat buildup and potential tire failure. Even a small percentage change in ambient temperature can significantly affect tire pressure.
What do technicians look for during inspections?
They check tread condition carefully, looking for specified wear limits, cuts, especially cuts across tread ribs, embedded objects, bruises, or bulges, which might indicate internal damage or ply separation. They also inspect the sidewalls for damage. Any damage beyond defined limits means the tire must be removed.
Is there a major safety concern when changing tires?
Yes, a huge one. Because aircraft tires are inflated to very high pressures, they store enormous potential energy. A damaged or improperly assembled wheel tire can explode with lethal force. The absolute #1 rule is always fully deflate the tire before attempting to remove the wheel assembly from the aircraft or disassembling the wheel halves.
Always deflate first. Got it.
And when inflating a newly assembled tire, it must be done inside a reinforced safety cage using regulated pressure from a safe distance. Safety procedures are paramount when dealing with aircraft tires.
Okay, let's talk about fuel, the lifeblood of the aircraft. Managing it must be more complex than just filling up the tanks.
Much more complex. The primary job of the fuel system is simple in concept. Deliver an uninterrupted flow of clean, contaminant-free fuel to the engines under all flight conditions and attitudes. But achieving that reliably and safely involves a lot of engineering.
Where is the fuel actually stored? In separate tanks?
On most large aircraft, the primary fuel storage is in integral wing tanks. This means sections of the wing structure itself, the spars, ribs, and skin are sealed to form fuel-tight tanks.
The wing is the tank.
In large part, yes. This is very efficient structurally, using existing space. Because these tanks are long and wide, they contain baffles and check valves to limit fuel sloshing during maneuvers. Some aircraft might also use bladder tanks' flexible, removable fuel cells placed inside a structural cavity, perhaps in the fuselage center section or tail.
What safety features are built into these tanks?
Several key ones. Each tank must have an expansion space, usually at least 2% of the tank volume, to allow fuel to expand if temperature increases without overflowing. They need sumps at the lowest point with drain valves to collect water and contaminants for draining. Vents are crucial to allow air to enter as fuel is used, and to vent air or fuel vapor out during refueling or due to temperature changes, preventing pressure buildup or vacuum. And fuel system independence is vital. Ideally, each engine should have its own independent fuel supply path from the tanks.
How does the fuel get from the tanks to the engines?
It involves a network of fuel lines, valves, and pumps. Inside the tanks, you typically find electric boost pumps. These are usually centrifugal pumps submerged in the fuel.
Why submerge?
They push fuel out of the tank under positive pressure. This ensures a steady supply to the main engine-driven fuel pumps, which are usually high-pressure pumps mounted on the engine itself, prevents vapor lock, fuel boiling at low-pressure shy altitudes, and allows fuel transfer between tanks.
What about keeping the fuel clean?
Fuel filters are critical. There are usually multiple filters in the system designed to remove microscopic particles. They often have a bypass valve feature.
What does that do?
If the filter gets completely clogged, say by ice or heavy contamination, the bypass valve opens to allow fuel to flow around the filter element, ensuring the engine doesn't starve. This would usually trigger a warning light in the cockpit, telling the crew the filter needs attention.
How is fuel managed between different tanks during flight to keep the plane balanced?
That's done using cross-feed and transfer systems. By opening and closing specific valves and running selected boost pumps, pilots, or automated systems, can move fuel from one tank to another or feed an engine from a tank on the opposite side of the aircraft. This is essential for maintaining lateral balance as fuel is consumed unevenly or for managing the aircraft's center of gravity.
Center of gravity. Fuel affects that.
Massively, especially on large aircraft with fuel stored way out in the wings and possibly in a central or tail tank. Some advanced aircraft have computerized center of gravity control systems, CGCC. These automatically monitor fuel quantity in each tank and transfer fuel fore or aft during the flight to keep the CG within the optimal range for maximum efficiency and stability.
That's clever. How do pilots know how much fuel they have?
Fuel quantity is usually measured using capacitance-type indicating systems. These use probes extending down into the tank. The fuel acts as a dielectric material between pleats in the probe. The capacitance changes proportionally to the fuel level.
Why capacity?
It has no moving parts inside the tank, making it very reliable. Multiple probes are used in each tank, and their readings are electronically processed to give an accurate total quantity, even when the aircraft is maneuvering and fuel is sloshing.
What about fuel contamination? Water seems like a big risk.
It's the most common contaminant. Water can get in through condensation or during refueling. It tends to settle at the bottom of tanks in the sumps. At altitude, this water can freeze into ice crystals, which can block filters or fuel lines.
How is it dealt with?
Regular draining of tank sumps and system filters is the first line of defense. Fuel samples are visually inspected for water and sediment. Water-detecting paste can be used on dipsticks, or electronic water detectors might be installed. Additives like anti-icing agents are often blended into jet fuel to prevent dissolved water from freezing. Other contaminants like solid particles, dirt, rust, and even microbiological growth, bacteria and fungi that live in the fuel-water interface, are also concerns that require monitoring and treatment.
Okay, beyond fuel and electricity, hydraulics provide the real muscle, right?
Right.
Moving big, heavy things.
Absolutely. Hydraulic systems generate, transmit, and control power using pressurized fluid. They operate high-force components like landing gear, flaps, spoilers, thrust reversers, flight controls on larger aircraft, nose wheel steering, and brakes.
What kind of pressures are we talking about?
Typically very high. Common operating pressures in large aircraft are around 3,000 psi, and some newer systems operate at 5,000 psi. This allows relatively small actuators to generate enormous force. Because these systems power critical functions, they are designed with multiple independent systems for redundancy. A large airliner might have 3 separate hydraulic systems, e.g. left, right, center, or blue, green, yellow.
What fluid do they use? Is it just oil?
It depends on the aircraft type. Older or smaller aircraft often use mineral-based hydraulic fluid, typically red, like MILH 5606. However, most commercial transport aircraft use fire-resistant phosphate ester-based fluids, the most common brand name being Skydrol, typically purple.
Why fire resist?
Because hydraulic lines often run near hot engines or electrical components. A leak of flammable mineral oil could easily start a fire. Phosphate ester fluids have much higher auto-ignition temperatures, significantly reducing that risk.
Are these fluids compatible? Can you mix them?
Absolutely not. This is a critical point. Mineral-based and phosphate ester fluids do not mix and will damage the seals designed for the other type. Even topping up a Skydrol system with the wrong fluid can contaminate it and require a complete system drain, flush, and potentially seal replacement. Seals are specific neoprene or Buna-N for mineral oil, butyl rubber or ethylene propylene for phosphate esters. Maintenance personnel must be extremely careful about using the correct fluid type.
Cleanliness must be vital too, with those pressures and tight tolerances.
Paramount. Hydraulic systems are very sensitive to contamination. Dirt, water, or metal particles can cause valves to stick, damage pumps, and clog filters. Maintenance requires extreme cleanliness. Clean tools, clean work areas, capping lines immediately upon disconnection, using approved solvents for cleaning parts. Filters are installed throughout the system in pressure lines, return lines, pump case drains to capture contaminants. Filter elements have specified replacement intervals.
Where's the hydraulic fluid stored?
In our reservoir. This holds the supply of fluid for the system. Reservoirs can be non-pressurized on simpler systems, but on high-altitude aircraft, they are typically pressurized using bleed air or system pressure.
Why pressurize the reservoir?
To ensure a positive flow of fluid into the inlets of the main hydraulic pumps, even at high altitudes where ambient pressure is low. This prevents pump cavitation, formation of vapor bubbles, which can damage the pumps. Reservoirs also accommodate fluid volume changes due to temperature or actuator movement and often incorporate sight gauges or quantity transmitters. Some have standpipes to ensure a reserve amount of fluid is available for essential systems, like brakes or emergency flight controls, even if a leak drains the main supply.
How is the high pressure generated?
By hydraulic pumps. Aircraft usually have multiple engine-driven pumps as the primary source, typically mounted on the engine accessory gearbox. There are also often electric motor-driven pumps, EMDPs, for backup, ground operations, or sometimes as primary pumps on newer, more electric aircraft designs. Hand pumps might be included for emergency or ground servicing.
What type of pumps are they?
Piston pumps are very common in high-pressure systems, like axial inline or bent axis designs. These use multiple pistons moving back and forth in a cylinder block to deliver a continuous, relatively pulse-free flow of high-pressure fluid. Many main pumps are variable displacement pumps.
Meaning they can change their output.
Exactly. They have an internal mechanism, often controlled by a compensator valve, that automatically adjusts the pump's displacement, the amount of fluid pumped per revolution, to maintain a near-constant system pressure. When system pressure reaches the target, say 3,000 psi, and there's no demand, the pump reduces its flow to nearly zero, minimizing wasted energy and heat generation. Engine-driven pumps usually have a shear shaft designed to brake if the pump seizes internally, protecting the engine's gearbox from damage.
And how is that high-pressure fluid directed to make things move?
Through a network of control valves. Selector valves, often electrically controlled solenoid valves or manually operated, direct the fluid flow to the desired actuator and determine the direction of movement. Check valves allow flow in only one direction. Sequence valves control the order operations. Shuttle valves allow a system to be pressurized by more than one source, for example, normal and emergency. Actuators are the devices that actually convert hydraulic pressure back into mechanical force, usually linear actuators, cylinders with pistons, or rotary actuators.
What keeps the fluid from leaking out, especially around moving parts like actuator pistons?
Seals, primarily O-rings. These are ubiquitous in hydraulic systems. They require careful inspection for nicks or damage, proper lubrication before installation, and care to avoid twisting or stretching them over sharp edges. Backup rings, usually made of Teflon, are often installed with O-rings in high-pressure applications to prevent the O-ring from being extruded into the gap between moving parts.
Okay, let's talk about weather hazards. Flying into an ice storm sounds terrifying. How do aircraft cope with ice and rain?
Ice accretion is a major hazard. Even a thin layer of ice, snow, or frost, especially on the leading edges of wings and tail surfaces, can severely disrupt airflow. It reduces lift, increases drag dramatically, increases the stall speed, adds weight, and can interfere with the movement of flight controls or freeze sensors.
So how is it detected and dealt with?
Modern aircraft have sophisticated ice detection systems, often using vibrating probes or optical sensors that alert the crew when icing conditions are encountered. Then, ice protection systems are activated. It's important to distinguish between anti-ice systems, which prevent ice from forming, and de-ice systems, which remove ice after it has already formed.
Let's start with anti-icing. How do they prevent ice building up?
The most common method on turbine aircraft is thermal anti-icing using hot engine bleed air. For wing anti-ice, WAI, this hot air, which might be temperature regulated first, is ducted along the leading edge of the wings, usually through piccolo tubes that spray the hot air against the inside surface of the leading edge skin, keeping it warm enough to prevent ice adherence.
What about the engines themselves? Ice ingestion sounds bad.
It's critical to prevent. Engine anti-ice, EAI, uses bleed air to heat the engine inlet cowl lip and sometimes internal guide vanes. This is often automatically activated by the ice detection system, or manually selected by the pilots, often used proactively when flying invisible moisture below certain temperatures. Other areas like flight deck windows and critical sensors, pitot tubes, AOA vanes, temperature probes are typically anti-iced using electric heating elements.
What about de-icing, removing ice that's already there?
The classic system, still common on many turboprops and some business jets, is pneumatic de-icer boots. These are inflatable rubber boots bonded to the leading edges.
How do they work?
They have internal tubes that are rapidly inflated with pressurized air from bleed air or a dedicated pump, causing the boot to stretch and expand. This cracks and breaks off the accumulated ice, which is then carried away by the airstream. The boots inflate and deflate in cycles, often alternating between different sections.
What about on the ground before takeoff? You see planes getting sprayed?
That's ground de-icing and anti-icing. A two-step process might be used. First, de-icing fluids, often heated Type I fluids, usually orange, are sprayed to remove existing snow, ice, or frost. Then, if precipitation is still occurring or freezing conditions exist, a thicker anti-icing fluid, Type 2 or 4, often green or yellowish, is applied.
What's special about the anti-icing fluid?
These fluids, especially Type 4, contain thickeners that make them thixotropic. They form a gel-like coating that adheres to the aircraft surfaces and provides protection against refreezing for a certain period, called the holdover time. This holdover time depends critically on the fluid type, mixture concentration, ambient temperature, and the type and intensity of precipitation. When the aircraft accelerates for takeoff, the airflow shears the fluid, causing it to flow off the wings.
And rain. Just windshield wipers.
Windshield wipers are common, similar to car wipers, but usually more robust and faster. However, at high speeds, the airflow can lift the blades off the glass, reducing effectiveness. Some aircraft also use a chemical rain repellent coating on the windshields that causes water to bead up and blow away easily. Older systems sometimes used a pneumatic system that blasted high-velocity air across the windscreen to clear water.
We've talked about bleed air a lot. Are there other uses for pneumatic and vacuum systems?
Yes, air pressure, both positive and negative vacuum, is used for various tasks. Simple vacuum systems, often driven by engine pumps or venturists, were traditionally used to power gyroscopic flight instruments on smaller aircraft, though electric gyros or AHRS are more common now.
And pneumatic systems using positive pressure.
We distinguish between different pressure levels. We've covered medium pressure pneumatic systems extensively using engine bleed air, typically 35 to 150 psi, for engine starting, anti-icing, air conditioning, etc. There are also high-pressure pneumatic systems, often using stored compressed air or nitrogen bottles at maybe 1,000 to 3,000 psi.
What are those used for?
Often for one-shot emergency operations, like emergency landing gear extension or emergency brake application, if the hydraulic systems fail. Sometimes high-pressure nitrogen is used to pressurize a hydraulic accumulator for these purposes, a sort of hydraulic system. Some aircraft might have onboard compressors to recharge these high-pressure systems.
Okay, last systems area, the basic amenities. Water and waste systems, essential for passengers.
Absolutely. Potable water systems provide clean drinking water for galleys and lavatories. Water is stored in tanks, which are typically pressurized using regulated air pressure, maybe 2050 psi, to ensure water flows to the taps even when the aircraft is on the ground or at low altitude. Water lines running through unheated areas are electrically heated to prevent freezing. There's usually a single external servicing panel for filling and draining the tanks.
And wastewater from sinks.
Wastewater from galley and lavatory sinks usually drains overboard through heated drain mass on the underside of the fuselage. Check valves prevent cabin air from escaping or odors from coming back up. Cabin pressure differential helps force the water out at altitude.
What about the toilets themselves?
Older systems use recirculating fluid, blue juice. Most modern aircraft use vacuum toilet systems.
How do those work?
When flushed, a valve opens connecting the toilet bowl to a vacuum line. Suction pulls the waste into a central holding tank located elsewhere in the aircraft. A small amount of potable water is used to rinse the bowl. The vacuum is generated either by an electric vacuum blower, primarily used on the ground or at low altitudes, or above a certain altitude, for example 16,000 feet, simply by the pressure differential between the cabin and the low outside air pressure. A barometric switch often controls when the system switches from the blower to differential pressure. It's efficient and uses very little water.
The future of aviation onboard systems and integrated avionics.
Let's talk about how aircraft are getting smarter. It almost feels like they can diagnose themselves now. How does that work?
That's the realm of onboard maintenance systems, OMS, or central maintenance systems, CMS. Their purpose is exactly that: to monitor aircraft systems, detect faults, record them, and provide troubleshooting guidance to maintenance crews.
So they tell technicians what's wrong.
Yes, and often how to fix it. They can advise the flight crew of system faults during flight, usually via messages on the ACAS or ECAM displays. On the ground, maintenance personnel can access the system, typically through a central maintenance computer CMC interface.
What can they do with the CMC?
They can review fault histories stored in non-volatile memory, initiate system self-tests, built-in test equipment, and get diagnostic information. Many components, line replaceable units or LRUs, have their own byte indicators, often simple lights showing status. Some systems even allow for fault data to be automatically downlinked to the airline's maintenance base while the aircraft is still in the air, or immediately upon landing via ACARS or other data links.
And no more paper manuals being lugged around.
Increasingly, yes. OMS often includes electronic data storage for maintenance manuals, wiring diagrams, illustrated parts catalogs, flight manuals, etc. Technicians can access this information directly on laptops or terminals connected to the aircraft, allowing for quick searching, viewing, and sometimes even printing specific pages or reports directly from the aircraft. Boeing's Maintenance Access Terminal, MAT, is an example.
That must save a lot of time and weight. Now, related to this integration, how are modern aircraft designs reducing the sheer amount of hardware? The boxes, the wires needed for all these complex systems.
That's a major trend driven by integrated modular avionics, IMA architecture. It's a fundamental shift away from the older federated architecture.
Federated architecture, what's that?
In a traditional federated system, almost every avionics function, say the VOR navigation system, the autopilot computer, the fuel quantity system, had its own dedicated box, RU, its own power supply, its own controls and indicators, and lots and lots of dedicated point-to-point wiring connecting everything.
Sounds heavy and complex.
Extremely. Lots of duplication, weight, power consumption, and potential points of failure. IMA changes that paradigm.
How?
The core concept of IMA is shared resources and common hardware platforms. Instead of dozens of unique boxes, you have a smaller number of powerful, standardized computer modules, often called core processing input-output modules, CPIMs, or similar names.
And these modules do multiple jobs.
Exactly. A single module might host software applications for several different functions, maybe landing gear control, fuel management, and cabin pressure control running independently, but sharing the same processing hardware, memory, and network connections. They also share common resources like power supplies and data buses, like ANC 664 AFDX, which is like an aviation-specific Ethernet.
What are the benefits of that?
Huge advantages. Significant reduction in bulk and weight due to fewer boxes and much less wiring. Improved fault tolerance because functions can potentially be rehosted on spare modules if their primary module fails, and redundant power supplies support multiple modules. And generally increased reliability due to fewer components and standardized, rigorously tested hardware and software platforms based on standards like ANC 653, which ensures different applications running on the same processor are safely partitioned from each other.
So it's like cloud computing, but inside an airplane.
That's actually a pretty good analogy in some ways. Shared resources, virtualized functions running on common platforms. It's the direction modern aircraft design is firmly heading.
What about inside the cabin? All the entertainment, communication, lighting systems, how are they managed?
Those fall under cabin systems. Modern aircraft use sophisticated digital networks to control and integrate these functions. The Cabin Intercommunication Data System, CIDS, often acts as the central interface, connecting the flight attendant panels, passenger address system, interphone, and various cabin electronics controllers.
And the entertainment.
The in-flight entertainment, IFE system, providing movies, music, maps, etc., is a major part. There's often a cabin network service involving servers that manage content delivery, potentially provide internet access via satellite or ground links, and interface with passenger service units, reading lights, call buttons, and seat electronics, screens, controllers, power outlets. Systems like ANC 628 define standards for these cabin networks.
It's a whole flying network operations center back there.
Pretty much, managing everything from boarding music and pre-recorded announcements to individual passenger video streams and potentially onboard Wi-Fi connectivity.
And finally, the move towards the paperless cockpit. How has technology changed information access for the crew?
Primarily through the electronic flight bag, EFB. This has revolutionized how pilots access information.
Is it just an iPad with some apps?
It started that way, but certified EFBs are much more integrated now. They can be portable devices or installed displays in the cockpit. They replace bulky paper flight bags containing charts, approach plates, manuals, performance calculations, checklists, logbooks.
What can they display?
Electronic aeronautical charts, often showing the aircraft's real-time position overlaid, airport diagrams, digital flight manuals, minimum equipment lists, MELs, weather information, performance calculations, electronic checklists, even potentially video from exterior cameras or flight deck entry surveillance. It saves enormous weight, ensures information is always up to date, and improves situational awareness and efficiency. Flight attendants are also increasingly using tablets for their manuals and passenger information, again saving weight and improving access. Outro.
So there you have it, quite a journey through the incredible engineering and the, well, frankly, mind-boggling systems that make modern air travel possible.
It really is something when you break it down.
From those invisible aerodynamic forces lifting tons of metal, through the intricate structures designed for damage tolerance, the vital environmental and fire safety systems, right up to the complex digital networks running the avionics and maintenance systems, it truly is a marvel. There's a real elegance in the precision and redundancy built into it all.
There absolutely is.
Yeah.
And what always strikes me is how every single component, no matter how seemingly small or simple, plays a crucial role in the overall safety and efficiency of the aircraft. It's an incredibly interconnected system.
It really is.
And, thinking about all this integration, especially the move towards IMA and more powerful onboard diagnostics, it really raises an interesting question for the future, doesn't it?
How so?
Well, as these aircraft continue to integrate even more systems, rely more heavily on digital control, and become increasingly self-aware through OMS, how is that going to change the dynamic, the interaction between the human and the machine?
You mean for pilots and technicians?
Exactly. How does the role of the pilot evolve in an increasingly automated cockpit? And how does the role of the maintenance technician change when the aircraft itself is providing so much diagnostic data? It's this continuous evolution of the human-machine partnership in aviation.
That is a powerful thought to consider. Where does the human expertise fit in as the machine gets smarter? Fascinating stuff. Well, thank you for joining us on this deep dive into the intricate world of turbine airplanes.
My pleasure.
We hope you, listening in, feel a little more well-informed now about these complex machines that connect our world. Maybe you'll even appreciate the hums and whirs on your next flight just a little bit more.
Hopefully.
Until next time, keep digging for those nuggets of knowledge.